And we're back. Welcome back and happy Tuesday. Today we will continue on with routing, specifically distance vector routing, and then we'll examine how you abstract large groups of routing infrastructure into subgroups that we call areas. Okay, so before we begin, some administrative bits. Project number 4, our TCP Wireshark, is due this evening, Tuesday, the 30th at 11:59 and 59 seconds, 1 second before the stroke of midnight. So where we last left off, we talked about link state routing, and specifically, we gave 2 examples of Dijkstra's algorithm. Once Dijkstra's algorithm converges, we assemble all of the predecessors from Dijkstra's algorithm into the shortest path tree, and it's this shortest path tree that we use to determine what link to employ for a particular destination address, and that's used to set the forwarding table for the node that ran this Dijkstra's algorithm, this routing algorithm. And in this case, the source node in question was node or router U. Okay, so let's continue on. And we're going to look at distance vector routing algorithms. And these distance vector routing algorithms, or routing protocol, are decentralized. And the key upon which these distance vector routing algorithms are based are a dynamic programming method based on the Bellman-Ford update equation. Now, in this, let's define some terminology. We start with little d sub x of y, and that's going to be the cost of the least cost path to go from source or starting node x to destination node y. So then when we try to calculate what this d sub x of y is, it's the minimum neighbor v such that the cost between x and that neighbor plus this cost from the neighbor to the destination y is the smallest. So what actually does this Bellman update equation mean? So suppose we start out with source node we'll call x, and x has some neighbors in the network graph, so they're directly connected, they share a connection with router x. So we have x's neighbor, let's call that first one v1, and we call the next one v2, and let's say it has some number of neighbors up to and including, let's just call that v sub k. Now, of course, if we go to each one of these neighbors from x, each one of these neighbors has associated with it this d sub neighbor with a target or destination of y. So here's node y, and we know we have some distance on the least cost path from x's first neighbor v1 to y. So we call that d sub v1 of y. Likewise, we have a least cost path from v2 to y. Let's call that distance d sub v2 of y. And then lastly, we have that least cost path from x's neighbor vk to get to y as our wiggly path. Let's call that d sub vk of y. So now what this Bellman-Ford equation does, it says, okay, if I want to get from x to y, d sub x of y, I can do that by going through some neighbor to x such that the cost of going from x to each neighbor b plus that distance from that neighbor to y is going to be minimal. So we take one hop at a cost and add that to the distance of the least cost path from that neighbor to y. And we consider each one of those neighbors to try to see which one is the intermediary along the least cost path, consisting of the sum of the link from x to that neighbor, b sub k, plus that distance from that neighbor to y. And that's exactly what this Bellman equation is doing. It's considering which one of these neighbors, v, is the correct one that leads to the minimum one hop plus distance to get to y. All right, so let's take a look at the Bellman-Ford update as it pertains to this network involving routers or nodes in some system U, V, W, X, Y, and Z. And so here, if we take a look at this, well, let's look at node U. If we want to get from U to Z, well, let's consider all the neighbors of U. We have U's neighbor W, we have U's neighbor V, we have U's neighbor X. Now, of course, for each one of these neighbors, let's consider that least cost path distance to get from each neighbor to Z. So let's look at U's neighbor V. Well, to get from V to Z, that least cost path is going to be 5. And I'm going to draw that squiggly line. So we squiggle down this way, we squiggle that way, and we squiggle that way. That's 2 plus 1 plus 2. There's our 5. So that's going to be our D sub V of Z, which is equal to 5. So then let's look at U's neighbor X. If we go from X to Z on the least cost path, that's a squiggly line. That's 1, 2. That's going to be 3. So that's going to be D sub X of Z. And then lastly, if we look at U's other neighbor, W, well, this, we're going to draw another squiggly line. So we're going to go down here, down up there, for a cost of 1 plus 2, that's 3. That's going to be D sub W of Z. So now, if we want to find D sub U of Z, we're going to go intermediate between one of U's neighbors, and then from that neighbor on the least cost path to get to Z. So we have the cost of U to V plus that D sub V going to Z. And then we can go indirectly from U to X, cost of 1 by that link, and then from X, D sub X of Z, get from X to Z at that cost. And then lastly, we could go indirectly through U's neighbor W at a cost of 5, and then this D sub WZ, total cost of 3 to get to Z. So if we fill in these values, going indirectly through V, then from V to Z along the least cost path, that's 2 plus 5, which is 7. To go indirectly through X, that's 1 plus 3, that's 4. And then to go indirectly through W, that's 5 plus 3, which is 8. And so the cheapest alternative here is to go indirectly through X. So we're going to take this U to X for a cost of 1, and then cost of 3 to get along the least cost path from X to Z. So we're going to call that cost 4 because 1 plus 3 is 4. All right. So we have in this scheme the need for a node to add up not only the link that it shares with its neighbor, that link cost, but also that least cost path estimate from its neighbor to get to that destination node. Now, in order to do that, a node U that computes that, it has to know what all of these least cost path distances is for each one of its neighbors in order to do this computation for the Bellman-Ford update. Now, these estimates are called distance vectors, hence the name distance vector routing protocol or algorithm, and this consists of values D sub X targeted of Y. Now, D sub X targeted Y is the estimate of the least cost path to get from X to Y. Now, X is going to maintain a distance vector, and this distance vector is going to be an estimate. It's an estimate because it gets refined, but this estimate is going to include in X this least cost estimate to get from X to every Y, where Y is every single node in the network. And so X is going to have an estimate to say how much does it cost to get from me to every other node in the network, including myself, and that cost, of course, is going to be 0. So for each node, let's call it X, it knows the cost of the one hop path, that link that it shares with its neighbor. That's just the edge cost, C of X to V. for each of X's neighbors V, but it also maintains a copy of its neighbor's distance vectors, and that's how it's able to run this Bellman update equation. So for each neighbor of X, X has a neighbor V, so here's X. Here's X's neighbor V1 and V2, for example. Now, X is going to get a copy of V's distance vector, D sub V, to get to each one of those nodes in the network from V. And so once X gets all of these distance vectors from its neighbors, it can then evaluate using the link cost plus the distance vector of its neighbors, D sub V, D sub X, D sub W, in order to compute which neighbor is most fruitful to go through as an intermediary to get to that destination node Z. Okay, so let's look at our key idea here. From time to time, each node is going to send its distance vector estimate to each of its neighbors. Now, when a node X receives a new distance vector estimate from a neighbor, that means some distances have changed. So what it's going to do, it's going to update its own distance vector using the Bellman-Ford update equation now that it knows the distance vectors of its neighbors. So what does it do? It says, okay, my new distance vector is going to be the minimum, because it's least cost path, the minimum neighbor V, such that the one hot distance plus my neighbor's distance vector estimate to get to Y is the smallest. Okay. Now, under certain conditions, this distance vector estimate to get from node X to any target node, any other node in the network, that's going to converge to the actual least cost path. It takes some time because costs will change, distance vectors get sent out, and node, or link rather, costs will also change. And so this approach, distance vector routing, is iterative. It goes in a series of rounds, updating until convergence. It's also asynchronous because there's no continuous clock that's guiding the progress of this algorithm for all of the nodes or routers on this router infrastructure, this router network. And so because it's decentralized, it updates incrementally by exchanging information, and this information is the distance vector. And so the local links cost can change. That's one thing that can trigger this algorithm running. And also you can get a distance vector update message from your neighbor. That means that something has happened with the cost, so you have to update your cost because you're going indirectly to the destination through one of your neighbors. This is also distributed, and each node is going to notify its neighbors only when its distance vector changes, and then your neighbors, they notify their neighbors, and their neighbors notify their neighbors, and so this information eventually washes across the network. So what does each node do, each router? They wait for a change in either a local link cost or a distance vector message, also called sometimes a router message, distance vector update, from its neighbor. And when one of these two things happens, it recomputes its own estimate, and then if that recomputation of its own estimate results in a change to its distance vector, then it sends it to each one of its neighbors. Okay, so let's take a look at an example. It's a simple example, but it certainly illustrates all of the components associated with distance vector routing. So here we have a very simple router network. We have three routers, X, Y, and Z. X shares an edge with Y and Z at a cost of 2 and 7 links. Y shares an edge with X and Z at a cost of 2 and 1 respectively. And lastly, Z shares a link with X and Y at a cost of 7 and 1 respectively. So here we start out, and in the beginning, each node only knows the link cost that it shares with neighbors. And so this first table, that's node X, router X. Second one, that's router Y. And the third one is router Z. So here we have entries. The distance between X and X is 0 because it's itself. And then that link cost to get from X to Y is 2. And the link cost from X to Z is 7. So here for Y to get to X is 2. Y to Y is 0. Y to get to Z is a cost of 1, as we see here in this router network. And then lastly for Z, the cost to get to X is 7. The cost to get to Y is 1. And the cost to get to itself is 0. So now in the beginning, we have these vectors being updated, and the rest are infinity. And so X then sends its distance vector to node Y, its neighbor, and its other neighbor Z. Y sends its distance vector 201 to X and to Z. And lastly, Z sends its distance vector 710 to X and to Y. And so now that we get these distance vectors, let's take a look at how node X updates itself. It gets the 201 from node Y and the 710 distance vector from Z. So now X knows to get to X is always 0. So now it'll choose a new update for this entry, the distance to get from X to Y. So X has two neighbors. It has its neighbor Y and it has its neighbor Z. So if it chooses its neighbor Y, it goes through that link at a cost going from X to Y, and then you use that distance vector that it got from Y to look at the least cost path estimate to get from Y to Y. Well, to get from Y to Y is 0. So for that, we have 2, that link cost between X and Y, and 0, distance vector estimate to get from Y to Y. Likewise, to get from X to Y, you could also go through X's other neighbor, Z. So we take that link cost to go from that link XZ, that's a cost of 7, and then to get that distance vector estimate, least cost for Z to Y, is a link of 1, cost of 1. And that's this squiggly line, and there's that first hop. So we contrast the minimum between 2 plus 0, 7 plus 1, and we find that going indirectly through X's neighbor Y is much cheaper at a cost of 2. So we fill in a 2 there. So we also do the same calculation using the Bellman-Ford update equation for that entry to get the distance estimate for going from node X to Z. Now, to go from X to Z, we can go through one of X's two neighbors, going from X to Y, and then on to Z, or X to Z, and then the least cost path from Z to Z. So for the first one, going through X's neighbor Y, we have a cost of 2, and then the distance vector estimate from Y to Z is 1, so that's 2 plus 1 for a cost of 3. If we were to go through X's neighbor Z, the cost to get along that link from X to Z is 7, and then the distance vector estimate from Z to Z is 0. So 3 is smaller, so it'll be more advantageous, a cheaper or least cost path, smaller path cost, to go from X through to Z through X's neighbor Y. So we're going to fill in that 3 here, and we fill that in. And so we do this for all of the other nodes, and let's just briefly talk about node Y, and we'll also briefly talk about node Z. And so here, we had gotten originally the entry in Y. We got the distance vector from X, and we got the distance vector from Z. So now what we're going to do is fill in the new distance vector estimates for going from node Y to its neighbors X, Y, and Z. Now, from Y to Y is always 0. So if we go from Y to X, well, we go either through Y's neighbor X or through Y's neighbor Z. If we go through Y's neighbor X, that's a cost of 2, plus going the distance vector estimate from X to X, which is 0. That's 2 plus 0, which is 2. And then if we go through from Y to X through Y's neighbor Z, that's a cost of 1 to get through that link from Y to Z, and then the least cost path estimate from Z to X is 7. 1 plus 7 is 8. The 2 is cheaper, so we're going to go indirectly through Y's neighbor X. So to go from Y to X, we're going to go indirectly through Y's neighbor X at that cost of 2. So we write down 2 here. So then let's look at going from Y to Z. To go from Y to Z, we can go from Y to Z indirectly through Y's neighbor Z, or indirectly through Y's neighbor X. If we go indirectly through Y's neighbor X, well, that's the link cost 2 to get from Y to X, and then the least cost path estimate from X to Z is going to be 7. 2 plus 7 is 9. If we went indirectly from Y to Z through Y's neighbor Z, that's the link cost 1, plus the distance vector estimate from Z to Z is 0. 1 plus 0 is 1. It's cheaper to go from Y to Z through Y's neighbor Z. So we write down that 1. It's 2, 0, 1. Okay. So then lastly, if we look at node Z, well, node Z had gotten the distance vector from node X and had gotten the distance vector from node Y. And so we're updating the distance vector estimate for Z. So Z to Z is always 0 to itself. and now we evaluate going from Z to X. If we go from Z to X, that can go either directly through its neighbor X or through its neighbor Y. And we see to go through X, that's 7 plus 0. And if we go through Y, that's 1 plus the distance vector S from Y to X. That's 2. 1 plus 2 is 3. It's cheaper to go through Y. So we write down 3 here. Likewise, to go from Z to Y, we could either go through Z's neighbor Y, 1 plus 0, or Z's neighbor X, 7 plus the distance vector 2, or 9. So we're going to go through Y, and that's going to be a cost of 1. And so we'll notice here that when we did these updates, this vector for X, and we had this vector for Z, that changed, and this vector for X started out as 0 to 7, it changed to 0 to 3. But you'll notice here for this vector for Y, when we did the update, it did not change from the first round in this algorithm. So none of these distance vectors are going to be sent out. So Y is not going to send its distance vector, it didn't change. But X, because its distance vector changed from 0 to 7 to 0 to 3, it's going to send a copy of its distance vector to its neighbors, Y and Z. Likewise, node Z, its distance vector changed from 710 to 310, so it's going to send out its distance vector to its neighbors, which are its neighbors X and its neighbors Y. And so you see here in this third frame, we have 0 to 3, 201, 310. We have 0 to 3, 201, 310. And then we have 0 to 3, 201, 310. Okay, so this is an example of distance vector routing. And as you can see, it takes time. As updates happen, distance vectors get sent out, and that triggers the potential update of the neighbors to which those distance vectors were sent. All right. And so if we compare link state routing with distance vector routing, we see a lot of interesting differences. For the message complexity, link state routing, if you have n nodes and e links, remember this link state broadcast, each of those nodes is going to send messages along those e many links. So the complexity is big O of n times e, the number of nodes, times the number of edges, and that's due to the link state broadcast. Now, for distance vector, you only exchange messages between neighbors, and the convergence time is going to vary depending on these cascading updates as a result of updates to distance vectors triggering the send of distance vectors to neighbors. So we also look at the speed of convergence. For link state, we have nested loop. We're going for each node, looking at each of its neighbors, and so that's big O of n squared, where n is the number of nodes or routers in the network. And then each round requires some number of messages, so we have big O of n e messages, but this n squared rounds is due to that double nested while loop over this n many nodes. And you can have oscillations with this link state routing. Now, for distance vector, the convergence time can vary, and there could be some loops, routing loops. I send you my distance vector, you update, you send me your distance vector, I update, I send you my distance vector, you update, and you sort of have these loops of these updates triggering the sends back and forth. You also may have routing loops themselves, these loops. You can have a count to infinity problem. Count to infinity problem means that as you iterate and exchange these messages back and forth, these costs start increasing. Robustness, what happens if a router malfunctions? For link state routing, a node could possibly advertise an incorrect link cost. And so that would be fairly catastrophic, and each node only computes its own table. So if you advertise incorrect cost, then everyone gets this, they run their link state, and they have an incorrect or imprecise depiction of what the least cost paths should be. For distance vector, a node can advertise the incorrect path cost or advertise the wrong distance vector, send the wrong distance vector to its neighbors, and each node's table is used by the others, so these errors are going to propagate throughout the network. Okay, so let's take a look at intra-AS routing. Now, of course, we've kind of been very simple and idealized as it pertains to routing, and we've treated all routers as identical and the network is flat. And this is not true in practice. What happens in practice, because of the sheer number of router devices we have with several billions of destinations, you can't store all of those destinations in a routing table even if you use blocks of addresses. This would completely swamp the exchange of tables aggregations in your routing forwarding tables. And so, in addition, people who own and operate these routing networks, they want to have autonomy over the policies and the protocols and algorithms that they employ. And so when we talk about the so-called internet, what it is really a network of connected networks, a network of networks. And so each network has administrative autonomy and wants to have complete control over the routing for the network that they manage and they own and they operate. And so we aggregate routers into regions, and these regions are called autonomous systems, or ASes. Also, sometimes in the literature, you see the name routing domains. And so there are two different types of routing protocols, one that stitches together the routers in the same autonomous system in terms of establishing the routes and running these link state or distance vector routing algorithms, and the other is so-called Intra-AS Routing, and that's about establishing pathways between the seams where different autonomous systems connect to one another. So Intra-AS Routing is a routing among hosts within the same autonomous system or the same network of routers, and all the routers in a single autonomous system have to run the same intra-domain protocol. Routers in different ASes can certainly run different intra-domain routing protocols because that's at the behest of the administrator that sets up and runs and operates these autonomous systems routers. And so there's another router called a gateway, and this gateway router sits at the edge of its own autonomous system, and it has links both to the routers within the autonomous system as well as to a router or a couple routers that are in a different autonomous system. And so this inter-autonomous system routing is routing among ASes, and in this case, the gateways perform inter-domain routing as well as intra-domain routing. The inter-domain routing is establishing routes to get to all the other gateways so you can push packets into a different autonomous system. And the intra is once that packet makes it into the autonomous system, how do you get it to the right router within the same router network? Okay, and so in this picture, we have three autonomous systems. We have AS1, AS2, and AS3. Each one of them has some number of routers. Now, if we take into consideration a single router, such as router 1D, which is in autonomous system 1, it has a forwarding table, and this forwarding table is set by two different routing algorithms. One is the Intra-AS routing algorithm that establishes paths between routers in AS1, and the other is Inter-routing algorithm that establishes paths between the gateways at the seams between autonomous systems and AS1. And so in that case, for the Inter-AS routing algorithm, router 1B is a gateway router. It's at the seam that gets datagrams off to AS2, and then router 1C is also a gateway router. It gets routers between the seam onto AS3, between AS3 and AS1, and it goes across that seam between AS3 and AS1. Okay, and so the entries of the forwarding table are determined by two different routing algorithms, both the intra-autonomous system routing algorithm as well as the inter-autonomous system routing algorithm. Okay, so suppose then we have a router in AS1, and it gets a datagram, and this datagram has a destination that's outside of AS1. Well, the question then is, router should certainly forward that packet to a gateway, but which one should it forward it to? Well, what's going to happen here? Autonomous System 1 needs to learn which destinations are reachable through AS2 and which are reachable through AS3. And then it should take this reachability information and propagate it to all of the routers in AS1. And so that's the job of Inter-AS routing, is it looking at the reachability for autonomous systems that are outside of itself. That's Inter-AS routing. And so Intra-AS routing is known as an Interior Gateway Protocol. It's, or IGP. It's that routing algorithm that establishes paths for routers within the autonomous system. So we have interior gateways and we have border gateways. The border gateways are those at the border that connect to other autonomous systems. The interior gateways are those routers that are within an autonomous system. And so the most common Intra-AS routing protocol, one of them is called RIP, Routing Information Protocol, OSPF, open shortest path first, and IGRP, Interior Gateway Routing Protocol. Now, this last one was a proprietary standard for a long time from Cisco, and only until 2016 they decided to open it up and allow other people to see what they're doing. And so let's take a look at open shortest path first. It's publicly available. It's an open standard, and it uses link state routing. It is a link state routing algorithm. And so there's so-called link state packet dissemination, and you establish the topology, the set of all of the edge weights in the network at every single node. And the computation of routes is done using the same Dijkstra's algorithm that we talked about for link state routing. Now, the router in OSPF floods link state advertisements to all the other routers in the entire autonomous system. So they literally shout out around the network this link state information prior to running Dijkstra's algorithm to establish the path at each node in the network. And so these OSPF messages are carried directly over IP rather than TCP or UDP, and it has the link state for each attached link. And so there's ASes routing protocol. It's another standard, but it's nearly identical, very close to OSPF. And so security-wise, OSPF has some nice advanced features. Security-wise, all of these OSPF messages are authenticated to prevent malicious intruders to try to siphon off traffic off the network. And in OSPF, multiple paths that have the same cost can be allowed, whereas in RIP, you only can have one path with a single cost. And for each link, you can have different metrics for different types of services that you have to try to encourage various behaviors for the routing preferences, the path preferences. You can also have multicast in OSPF using the same topology data, and so it certainly has multicast support. And for very large aggregations of routers on a network, OSPF supports hierarchical aggregations. So let's take a look at these hierarchies, and hierarchies are how you make things scalable when you have a large number of devices. And so we have something called areas, and these areas are smaller aggregations of routers in OSPF. In this case, we have Area 1, Area 2, and Area 3, and each area has a set of so-called internal routers, and they route traffic around within an area. And then you have what's called an area border router. Now, these area border routers are responsible for stitching together areas into the so-called backbone. And so here in this blue region, we have within an area the border routers, and that gets traffic off of an area into the backbone. And then we have a set of routers interconnected in the backbone, and then we have what's called a boundary router that gets traffic onto and off of that entire autonomous system. And so this entire thing is one autonomous system, and the autonomous system subdivides its routers in this autonomous system into areas. In this case, we have 3 areas, and we stitch together these areas using the backbone routers, and the area border routers are how you get traffic onto and off of each area to and from the backbone. And then we attach the area to the network, this autonomous system, with a boundary router. So this boundary router is the border gateway for this hierarchical aggregation of the autonomous system using OSPF. And so we can have a 2-level hierarchy in OSPF. We have the local areas, more than one, and then we have the backbone. And link state advertisements are only within an area. Each node has detailed area topology and only knows the direction to networks in other areas. And so the area border routers, they summarize the distances to sub-areas, to its own area, but it advertises to other area border routers. And so these area border routers act almost like mini border gateway routers, but only among different areas within the same set of areas within the same autonomous system stitched together through the backbone routers. And the backbone routers run OSPF, but it's limited just to the backbone. So there's different domains, if you will, over which these routing algorithms are run. The backbone is separate from each one of the areas. And then the boundary router is connected to other autonomous systems. Okay, so with that, that's all I had to say about this hierarchical aggregation using Intra-AS Routing for OSPF, for aggregating groups of routers together in hierarchical fashion for much better increased scalability. With that, that's all I had for today, and we'll end there. As usual, please stay healthy, stay safe, and I'll see you all on Thursday.